Models of quantum computation. Today, it's actually not that much computation. Today, we do a little bit of background on contextuality and Bell inequalities and all of this, because we will later talk about contextuality as a resource. And so maybe it's a good idea to start out with what contextuality actually is. We start with this paper here, 1935. It's Einstein, Podolsky, and Rosen. Einstein was very unhappy with the structure of quantum mechanics and wanted to suggest an alternative theory. Yeah, and so he was trying to poke holes into the quantum formalism, standard quantum formalism. We see that. And so that's the birth of the idea of so-called hidden variable models. It's an alternative description for quantum phenomena. But the formalism is essentially classical, so there's just looks like classical statistical mechanics. Yeah, and they didn't prove such things existed, but they thought they might. And later this was proven not to be the case. So both the Bell inequalities, what the Bell inequalities do is they point out that depending on what model you choose, quantum mechanics or these hidden variable models, they make different predictions. So it's really, so you cannot make these hidden variable models reproduce the predictions of quantum theory. So that's what Bell pointed out. And then you can make an experiment and see what it decides in favor of. And then turns out you do not even need to make the experiment. So Kochen and Specker showed that these hidden variable models are internally inconsistent. They are not even properly defined. And we get to that. Okay, so that's the menu for today. Here's maybe the same in a little bit of a different way to arrange it. So this is a timeline. And it begins with Einstein, Podolsky, and Rosen, and it ends for us with the computational angle. So namely the inviolability to describe quantum phenomena with hidden variable models is a computational resource. I mean, the inviolability of hidden variable models, we will later call this contextuality, and that is a resource for quantum computation. So that is our subject for next time. This is what we really want to discuss, and we start up here just to make clear what we are talking about. So today, it's really on the fundamentals of quantum physics, beginning with that suggestion and ending with the experiment that distinguish between these models and quantum physics. And this is for next time. Einstein was very uncomfortable with the structure of quantum mechanics and all the probability in that formalism, and this is famously expressed in this sentence here, der alte würfelt nicht, the old man doesn't play dice. That's the beginning of what we want to talk about today. So here you have a little bit of reading material, or actually quite a bit of reading material, more than usual. So this is the Einstein, Podolsky, and Rosen paper, if you want to look it up. So we will fairly closely go by the text of the paper today. And then on the Bell inequalities, you have Bell's paper itself, but we will talk about a variant of the Bell inequalities that's easier for experiment, but also easier to talk about. So this is by Clauser, Horn, Shimoni, and Holt. Yeah, so that is what we will review today. And then there is the experiment. You may also want to look at that. Yeah, so much about the Bell inequalities. Then the Kochen-Specker theorem. You may check out the original paper, but we are not going by the original paper here because it's just too complicated, too hairy. David Mermin found later a slightly weaker but much simpler proof of the Kochen-Specker theorem. And we will look at that because it's really quite simple in the end. It is a weaker proof because it only holds in dimension 4 and up, whereas the original theorem holds in dimension 3 and up, Hilbert space dimension. Okay, but anyway, this is what we'll look at, and that's the original paper. Okay, so that is reading material if you want to. Okay, so now let's go through these parts. So can quantum mechanical description of physical reality be considered complete? So that was the paper title of Einstein, Podolsky, and Rosen. Yeah, so here, this is what Physical Review typesetting looked like in 1935. And what was the reason for this paper? Yeah, so I think we probably looked at this before. We have this weird feature of quantum mechanics that you can have spins sitting at spatially very far separated places like Earth and Moon, and these systems can nonetheless be entangled. And then if you measure one, you project the other. And that, in Einstein's way of thinking, didn't make the least bit of sense. And so he wanted to poke holes into quantum mechanics. And so he found something to object to. Yeah, you could question the correctness of the quantum mechanical formalism, but he didn't choose that. He chose to question something else. He chose to question the completeness of quantum theory. So by completeness, the question is, does the theory predict everything that is predictable? Or does it not speak about certain things? Okay, and so this was what he chose, or the three chose, as their angle of attack. So they wanted to question the completeness of quantum mechanics, meaning there could be an underlying theory that describes more than what quantum mechanics describes. And so now there's a bunch of terms to define. They needed to begin with complete. What does it mean to be complete? Then they said, okay, so whatever it means, we can provide a condition. So at least the following needs to be satisfied. So every element of the physical reality, so every observable thing, must have a counterpart in the physical theory. Every element in the reality must have a counterpart in the theory. So now what is an element of reality? So that is now also a term that needs to be defined. And so they say that if without in any way disturbing a system, and try to remember that, we'll later discuss what that might mean. Anyway, without in any way disturbing a system, we can predict with certainty, that is with probability of unity, the value of a physical quantity. Then there exists an element of physical reality corresponding to this physical quantity. So if we can predict it with certainty, then it is real. That is their explanation of what an element of reality is. Now comes a long piece of text. And so now so what they now do is they begin to talk about non-commuting observables. So they have two observables, A and B, that do not commute, and so that they cannot have simultaneously sharp values. Yeah. Okay, and so they say the wave function formula, essentially this is their argument here. So the wave function formalism says when the operators do not commute, then A and B cannot be simultaneously real. That's what the wave function formalism tells us. So Heisenberg uncertainty relation, essentially. Okay, and from this, it follows, they say that they have now two alternatives. Yeah? So either the quantum mechanical description, or let's begin with the second. So when the operators corresponding to two physical quantities do not commute, then the two do not have simultaneous reality. I mean, in real life, they do not have simultaneous reality because the wave function says they are not simultaneously real within the wave function formalism. But yeah, so something else could happen, and that is that there's something wrong with this formalism. So the formalism says that they are not simultaneously real, but that's just a shortcoming of the formalism. In reality, they are simultaneously real. And when that happens, then the quantum mechanical description of reality given by the wave function is not complete. So there is stuff out there that is real, even though the wave functions say it's not. Yeah? So these are the two alternatives that they remain with. Now they take and examine this in a particular setting. Yeah? So they try to get to grips with that. by considering a Bell state. And in fact, so we talk about a Bell state here because that's what we are now quite familiar with. The original Einstein-Podolsky-Rosen argument was with a different state. It was for a state that was entangled in position and momentum. And so this is a simpler version, and it's due to David Bohm. So I just want to acknowledge that we are now deviating from the EPR analysis and follow a simpler version by David Bohm. Okay, so what's considered here now is a Bell state, like so. We've seen this many times, and we know about the correlations in that state. So we know that this is a stabilizer state. You remember the stabilizer formalism of X tensor X and of Z tensor Z. And these properties we will now exploit. So we know that if we measure particle A in the Z basis, then it implies that if we measure plus, then we are projecting particle B in the state spin up. And if we measure minus, this implies that we are projecting particle B in the state down. And so this means it's now an eigenstate of the observable Z on B. Okay, and so according to the definition, so we can, after the measurement, we can predict this value with certainty. And that was how we defined, or how they defined, an element of reality. So they say this thing must be an element of reality. Yeah, and so now they can do the same thing for a measurement in the X basis. And remember, the protocol here, or the state, then implies that if we measure plus, we have the eigenstate with positive eigenvalue of X on particle B, and with outcome minus, we have the state with negative eigenvalue, particle B, state minus. Okay, so measurement of X projects particle B. Measurement of X on A projects particle B in these states. So as soon as that measurement happens, from the outcome, we can predict the value of XB. Yeah? And so that too is an element of reality. And so they say, okay, this is an element of reality, that is an element of reality. Still, that sounds odd because they correspond to non-commuting observables. But anyway, that's their conclusion. According to their definitions, they are both elements of reality. Yeah, they're both elements of reality, even if these observables do not commute. Okay, so now, yeah, so they continue, and this is now coming close to the end of the argument. So here they restate what they have previously reached. So they prove that either the quantum mechanical description in terms of the wave function is not complete. It was one alternative, and the other alternative was when the operators corresponding to two physical quantities do not commute, then the two quantities cannot have simultaneous reality. Okay, and so now they argue as follows. So they said, okay, we built our whole argument here on the wave function formalism. So let's assume the wave function formalism is complete. So let's assume alternative one is wrong. Yeah, one said wave function is not complete. Let's assume this is wrong. So the wave function is complete. Then everything that can be predicted follows from the wave function formalism. So we use this wave function formalism in this way. We apply the wave function formalism to this setting and arrive at the fact that both X and Z, even if they do not commute, correspond to elements of reality. Yeah, and now if we look at our alternatives, that is the negation of 2. So when alternative number 2 was, when the operators corresponding to the two physical quantities do not commute, the two quantities cannot have simultaneous reality. Okay, but we found that they did, according to those definitions. And so 2 is also wrong. So if we say 1 is wrong, this implies that 2 is wrong, and then we have no alternative left. So that cannot be, hence alternative number 1 must be correct. Yeah? And that is the quantum mechanical description of reality given by the wave function is not complete. Okay, so in fact the end of the argument. This is how they argued. And so now we come to the two last paragraphs of the paper. So here they just kind of, they of course know where the Achilles heel of their construction is, and they point this out explicitly in the second last paragraph. So let me read that to you. Indeed, one would not arrive, so I'm reading the highlighted part only. Indeed, one would not arrive at our conclusion if one insisted that two or more physical quantities can be regarded as simultaneous elements of reality only when they can be simultaneously measured or predicted. So remember the setting. You chose, or whoever, Alain Aspect chose to measure Z on particle A and would predict the element of reality ZA. He would choose to measure X on particle A, would choose in this way predict XB. So indeed, the reality of these observables is conditional on what's being measured. Yeah, so that's what they point out here. So physical quantities can be regarded as simultaneous elements of reality only when they can be simultaneously measured or predicted. The example there isn't of that kind. Okay, and then they continue. This makes the reality of P and Q depend upon the process of measurement carried out on the first system, which does not disturb the second system in any way. No reasonable definition of reality could be expected to permit this. Nowadays, we do not have any difficulty, kind of assuming such a kind of reality where this is actually happening. Yeah? So where this reality depends on the measurement on another particle. But yeah, so I'm just pointing this out to you. They knew the Achilles heel of their argument, but they still had this point of view. Now comes the last paragraph of the paper. And the last paragraph is this paper is the whole reason why we are looking at this today. And so the last paragraph says, while we have thus shown that the wave function does not provide a complete description of the physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. Okay, so let's see what that theory would be like. So this would be a theory in which we have these elements of reality, and those elements have values, and yeah, these values are now observable and predictable. But these values are not conditional, so they do not depend on measurement here and there. So these values are defined to begin with, since eternity. Yeah? Okay, so such is the kind of model that EPR think it exists. And yeah, and the question, is that true? And people have considered this. And this brings us to the second part of the lecture today, the Bell inequality. So this was the first thing where a distinction was made in the predictions between these hidden variable models, as they were called later, and quantum mechanics. So it's not the same. And then you can make an experiment. So let's talk about a hidden variable model. So what is it? So a hidden variable model has hidden states. So these states are hidden because you don't know what they are. It's like a statistical mechanics system. It's a spin configuration, and maybe you can read of the energy and so on and so forth, but you don't really know what state the system is in. Yeah? So there are these hidden states, and yeah, so that's the fundamental thing here. And so in every hidden state, every physically measurable observable has a definite value. Yeah, so that seems to be a hallmark of quantum systems. So when you measure an observable, you can only have certain values. And so now, and then if you measure a quantity twice, you find that you measure that same value again. So that looks like that this value has some reality. And so that is the assumption of the model. Yeah? So in every one of these hidden states, every observable has a definite value, like in classical systems. So I have a definite height. I don't know, the camera has a definite energy consumption. You have many examples. And of course, all these values are reproducible. Good. And so, but now we have to make sense of this quantum phenomenon that measurement outcomes are typically distributed according to some probability distribution. They are random. And this is modeled in this framework by the fact that these hidden states are distributed according to some probability distribution. So every one of these hidden states has a probability assigned to it. Yeah? And so this is how measurement outcomes become random in this model. And now the question is, can you describe physics with a model like this? Okay, and so now it turns out that the answer is no. So there are different predictions. So if you look at the same quantity from the angle of quantum mechanics and from the angle of such a model, you find that the predictions are different. Yeah? So this is what Bell pointed out, and then others after Bell. And in fact, we will look here at a slightly later result because it's easier to discuss. And then experiments were performed, and they decided in favor of quantum mechanics and against these hidden variable models. Good. Okay, so let's look at that. What we are looking at today is the setting of Clauser, Horner, Shimoni, and Holt. And it has two parties, A and B. And then for each party, we have two observables that we can measure. So maybe I try to draw this. So no line in between. Okay, so we have two parties, A and B, and they are potentially very far away. And then either party can measure in two settings. So here this would be A and A prime. And party B can also measure in two settings, and there can a priori be different observables B and B prime. So this is our setting. These observables are also of a special kind, namely they have eigenvalues +1 or -1, quantum mechanically speaking, so the values that you will measure are +1 or -1. And then we have a notation for these outcomes like so. Okay, so what does this notation mean? So there is an underlined observable. So A, say, is the observable itself. The underline is indicating that we're looking at the value corresponding to this observable at party A. Yeah, so this is really for the party. A underline means value, and this value depends on the choice of the measurement setting, A versus A prime, and it also depends on this hidden state, nu. Okay, good. Okay, so this is our notation for the measurement outcomes for those observables given a particular hidden variable model state. And so now we are looking at certain correlations. So there is one correlation is shown here. It depends on the measurement setting at A, measurement setting at B. Yeah, and so this is a correlation of measurement outcomes. And we are summing with the correct probability weight over all hidden states nu. So that's the correlation for these observables that you would measure in an experiment. And there's now 4 of these. So we can, so the first argument can be A or A primes, 2 choices. And the second argument here can be B or B prime, 2 choices for the measurement basis. So there's 4 combinations. So there's 4 such correlations now. And we are looking at a particular linear combination of these correlations. Yeah? So you see 4 as we expected, and you do indeed see that the measurement setting change from correlation to correlation. Good. And note, that's an important thing. So they are all added with a plus except one has a minus sign in front. And that will be important. So, and now the question is, what's the value of this composite correlation here? And we will show, so this is the part that we'll actually do here in class, that whatever the probability distribution over these value assignments is, for every hidden variable model, you predict that the magnitude of this quantity is 2 or smaller. Yeah? Whereas the quantum mechanical prediction is that the value can go as high as 2 times square root of 2. Okay, it's clearly outside this range. And so you can do the experiment for which quantum mechanics predicts this value. And then you'll see, is it quantum mechanical or is it describable by a hidden variable model? Good, so that's the plan. Yeah? So this is the version of the Bell inequality that these 4 people, Clauser, Horn, Shimoni, and Holt, proposed. And later the experiment was done and decided in favor of quantum mechanics. Let's just derive that. It's not very complicated. Let us do that, like here. So you remember just looking at one term. So the expression in terms of the hidden variable model is you have a value for this quantity, value for that quantity, dependent on the internal state. You have the correct probability weight here for these states, and then you sum over all internal states. Okay, this quantity you could call E A comma B nu. Yeah? So the value you would get for the HVM state nu. Okay? Good. And now, corresponding to that, we now define this correlation, it's actually defined up here. So we define this correlation value now dependent on the internal state nu. So what we will later do is we will, so the value for the correlation S as predicted by the hidden variable model is then the probabilistic mixture of all these S nus. Yeah, is that clear? Yeah, good. Okay, so this is the thing. So it is completely analogous to what we had before, but it is now with respect to any fixed given internal state nu, HVM state nu. It's called an ontic state, but that's just a word. Okay, good. So that's the thing now. And we can rewrite this expression now in the following way. So we find that the first and the second term both have the value capital A for choice of basis A in it. You have it here and you have it here. You have a minus in between. So we can write this as value, sorry, I think I forgot these underscores. Okay, so it's a simple transformation. We just pulled a capital A out in these 2 terms. And then when we look at the third and the fourth term, we see that they both depend on observable capital A for measurement basis A prime. And so, we pull that factor out. It's common to both terms. Gives us this. And so now in the brackets, over here, we have a difference of values, B, resulting from that minus. And over here, we have a sum of values, B, resulting from that plus. Okay, and so now tell me, what values can this difference have? So 2 and minus 2 we already heard, and 0, and that's really all, because individually they take values of 1 or minus 1. And so the same we have over here for the plus. Okay, so now tell me if you have 2 over here. What do you have over here? 0. And if you have -2 on the left, what do you have on the right? Also 0. Yeah, and that goes in reverse. If you have +2 for the sum, then you have 0 for the difference. And if you have -2 for the sum, then you also have 0 for the difference. So these are the possible pairings that you can have. So this means if you have something non-zero over here, then you have 0 over there on the other side. So it's only this term contributing or that term contributing. Yeah, it's only one of them ever contributing. Yeah, so one will contribute with certainty, and the other won't. Yeah, so this means that S nu is plus or minus 2. So that's the only thing that can happen. And so furthermore, this means, according to the hidden variable model, that the magnitude of S nu is 2 for any nu. So that is our first conclusion. So this is what the hidden variable model says. All right, and so now we have a little bit of triangle inequality. Yeah, so the triangle inequality is the first rule that we apply here. So we, so we take the sum outside. That is how we apply the triangle inequality. And so this is now smaller than sum over all states, magnitude of the probability times the value of S for that state. And that is equal to, since the magnitude, since the probability is positive, so this is equal to sum of the probability times the magnitude of this thing. And now we know from the previous slide that this is equal to 2 always. Yeah? And so this is equal to 2 times sum over all internal states, all untick states, p nu. And since we are dealing with a probability distribution, the sum over all untick states, the corresponding probabilities, there is 1, and so that thing is 2. So we have, we have a bunch of equal signs, but we have one smaller than or equal sign. And so the conclusion is that magnitude of S is smaller equal than 2. Okay, so this is our conclusion. This is the prediction of the hidden variable model. This is what every hidden variable model would predict without making any further assumptions. Okay, and now you can see what quantum mechanics says. And so this is a calculation that I let you do. I'm not going to do it here. So this inequality, has to apply to any such settings where we have these pairings of observables. So we define such a setting. And what does it mean to define such a setting? Well, we have to define a quantum state. We can choose any state we like. So we choose a Bell state. Maybe that's the one with the biggest violations. And then we choose 4 observables. So on party A, we decide to measure either Z or X. And on party B, the observables are different. So namely, there are superpositions of X and Z, once with a plus and once with a minus. Okay, and now if you just plug in these assignments to the into our correlation observable, then you find that the quantum mechanical value for that Bell state is 2 times square root of 2. Yeah? And that's clearly outside the range of what is permitted for hidden variable models. Yeah? So you measure, now in an experiment, you could measure that value and decide in favor of either quantum mechanics or hidden variable models. Good. Okay, and the experiment was performed in 1982 by Alain Aspect and collaborators, and the experiment showed ruled in favor of quantum mechanics. So the permitted range for hidden variable models was exceeded. By now, we have ruled out the idea of hidden variable models. So there are certain descriptions, certain physical situations of quantum mechanics that cannot be described in this way. And so we will continue with the Kochen-Specker theorem. So that shows that you wouldn't even need to do the experiment. So hidden variable models are internally consistent. Yeah, and that also, this contextuality according to Kochen and Specker is also what we need for our relation to quantum computation with magic states, so that we look at after the break. Part 3, so the remaining part, is about a similar thing. It is about the inviolability of these hidden variable models. But as I said, now this will not lead up to an inequality that you can test in an experiment, but it's rather an internal consistency that's being pointed to. Okay, so let's define the terminology. What is a hidden variable model even? So in the previous case that we looked at, the values or the observables that we assigned values to, they were local. They were either living in party A and party B. And then, having assigned values to those local observables, we would then conclude what values we would assign to correlations of these local observables. Okay, so the important thing is that the local observables at A and B, they necessarily commute because they live on different factors of the Hilbert space. Yeah? And so commutation is the basic notion, not locality. So if they are local, then on different parties they will necessarily commute. So for the contextuality discussions, it is commutativity that's the fundamental constraint here, not locality. So there will be local and unlocal observables that that will not matter. Yeah? So according to quantum mechanics, if we have a bunch of commuting observables, that we can measure them simultaneously. So commuting observables can have simultaneous values. So now we come to the definition of what a non-contextual hidden variable model is. Okay. So we have hidden variable model we have also already discussed. Now, what makes such a hidden variable model non-contextual? And it seems like in kind of a trivial assumption, but we will find that that's not so that things follow from it. So a hidden variable model is non-contextual if the value that we assign to any given observable is independent of what other commuting observables are measured jointly with it. Yeah? So it's only a function of the observable itself, and it does not depend on any of the other observables that we might also measure. We can measure an observable A jointly with an observable B. So this would be, say, context AB. And we can measure A jointly with some other observable C, and that would be the context AC. Yeah? And so we can do that if, so these are the preconditions, A and B commute, yeah, and also A and C commute. As soon as that is the case, we can measure simultaneously in this way. But it may also hold that B and C do not commute. Yeah? So they may indeed correspond to different measurement contexts, different measurement bases. Yeah? And so what we want is the value that we assign to the observable A does not depend on whatever else we measure jointly with A. So that's the assumption of non-contextuality. Yeah? And so now we want to investigate, are such hidden variable models viable? These non-contextual hidden variable models, are they viable? And so there is a theorem due to Kochen-Specker from 1967 that says, no, they are not viable, at least in dimension 3 and greater. Such models you will never get to work. And the original proof of this theorem is a little bit complicated. It involves 117 states in R3. Yeah? Beautiful picture, but maybe you don't want to go through all that. So we will indeed go for a proof that is much, much simpler, but also slightly weaker. So the proof that we are going to go through holds in dimension 4 and up. So we are missing dimension 3. Okay, but that proof is so simple that we can do it here in the lecture. This is the setting for the proof that we're actually going to do. So this is a proof in Hilbert space dimension 4. Okay, it's called Mermin square. So Mermin's paper, Mermin's Ref-Mod-Fis paper, is also one of the references given on the reading slide. Okay, so this is our setting here. So we have 2 spin 1/2 particles labeled 1 and 2, and we are now looking at 9 Pauli observables. And they group into 6 contexts. So the vertices in this graph here, they correspond to observables like Pauli spin flip X on particle 1 and so on and so forth. And these blue lines correspond to contexts. So context means these are commuting observables. So observables we can measure jointly. So you can, so we have 6 contexts here. You can check this for every context, that the observables that we have in those contexts, that they pairwise commute or can be measured jointly. Okay, but then there's more going on in these contexts. And you see this right here, for example. So if you multiply these observables together, you get the identity. And so this holds in all of the contexts except in one. So if you look at the context corresponding to the 3rd column, you find that these 3 operators multiply not to the identity, but to minus the identity. Yeah, in all the rows and columns, the observables multiply to the identity, except in the last column, where the product of the observables is minus the identity. And all the minus sign is what the proof is centered around. Yeah, and so we can measure every row or column here in this context. Not all rows and columns together, but every single one of them. So now what we are asking is, can we have consistent value assignments even for these observables? We're not even talking about probability distributions, but the question is, can we even have a single one value assignment for all of these things? Yeah? And so that's a precondition for having a hidden variable model. You need a set of states, nu, in that model. And the question is now, can you? Okay, so so now let's try to find that out. So before we look at that, we observe that we have a few constraints. So all the observables are of Pauli type, so they square to the identity, which means that the eigenvalues of these observables can only be plus minus 1. Yeah? And so then for these values of the hidden variable model, it must be the same, because the model is intended to reproduce quantum mechanics, so it must match that prediction, that first prediction of quantum mechanics. Okay, so we will have values plus minus 1 only. So furthermore, if we have 3 commuting observables A, B, C, It holds that if the product of the former is the third, then the corresponding values also satisfy this relation. So yeah, so the product of the two first values give the third value. Yeah, and the reason of that is if they commute, if these observables commute, then they can be simultaneously diagonalized, and then you find the eigenvalues on the diagonal. Yeah? So this relation holds. Again, this is a prediction of quantum mechanics, and so the hidden variable model must reproduce it. Otherwise, you could see the violation. Okay. Yeah? And if you have a relation like that, then the corresponding condition holds. Okay, so these are the two constraints that we find for the values of these 9 observables. Okay, so now okay, I already wrote that down. And it's a lot of writing, so I will not write it again. But so we will now use the constraints that we've just identified and set up a system of equations. So basically for now, we are dealing with the second constraint here. So this is, yeah, so an equivalent way of saying it is if A, B, C is the identity, then lambda of A, lambda of B, lambda of C equals 1. Yeah, it's the same thing. And that is how it is phrased over here. Yeah? So we have 3 commuting observables that multiply to the identity, and therefore their values must multiply to 1. Okay, so this was for the first context up here. So in second context, yeah? So the value for Z2 times the value of Z1 times the value of the correlated Zs, they need to multiply to 1 as well. So we find that right here. Yeah? So this is the constraint for the second row. Yeah? Constraint for the third row, yeah, value of this times value of that times value of this must be 1. Yes? This constraint here. Okay, so these were the rows. This is now for the columns. Yeah? So first column to the left, so value of x1 times value of z2 times the value of xz must be the identity. It's exactly what you have here. Value of x1 times value of z2 times value of xz is 1. Good. Okay, but the important column is the last one. So so we have the observables xx, zz, yy, and they multiply to minus the identity. So that's the thing. So the corresponding values multiply to minus 1. Okay, so this is our system of equations. And now we ask ourselves, does it have a solution? And it doesn't. That's very easy to see now. We multiply all of this. Yeah, multiply all left-hand sides, multiply all right-hand sides. Also have to agree. So the right-hand side is easily done. We have 1 minus 1 and plus 1 plus 1's otherwise, so the product is minus 1. So now we work out the products on the left-hand side. And for that, we're now using the other property that we have found, namely that the eigenvalues are all plus 1 minus 1. So the eigenvalues squared are plus 1. Okay, so meaning the values of the hidden variable model square to 1. And now we see, okay, now let's look how many times all these observables occur. So lambda of x1 comes up here and here. So it drops out. Lambda of x2 comes up here and here, drops out. And we can see this geometrically in this drawing up here. So every observable occurs in exactly 2 contexts, 1 row and 1 column. And so every value that we have here is squared. And so we get a 1 from from every observable. And so we have a contradiction. +1 equals -1. So we started from the assumption that a hidden variable model assignment lambda does exist, and we derived a contradiction. So this means that no such assignment can exist. Okay, so much about the idea of hidden variable models. So that's a simple proof of the Kochen-Specker theorem. I mean, it's much simpler, but also slightly weaker than Kochen-Specker's original proof. Okay, so much about that. We still want to connect a little bit better the notion of contextuality as discussed here in Mermin's square and the former notion of Bell non-locality. Yeah? So the idea that local hidden variable models failed. So we had two things, remember. We had the failure of local hidden variable models as witnessed by an experiment you can do, and we had the failure of contextual hidden variable models as an algebraic contradiction. So it's just as an inconsistency of any such model. Okay, so now let's make the two more alike. And so let's morph one into the other. And that can be done by way of Mermin's star. So Mermin's star is something very close to a Mermin square, but it can be morphed into something that looks more like a Bell inequality. And that's what we're going to do now. That's the last item for today. So yeah, so Mermin's star comes in a state-independent and in a state-dependent version. So the state-independent version is more like Mermin's square, and the state-dependent version is more like a Bell inequality. We will see that. Okay, so let's begin with the thing that's closest to what we just had so far. So we begin with the state-independent version. So this is now for 3 qubits rather than 2. Yeah, so you see this here. So we have these threefold correlated observable x on particle 1 times x on particle 2 times x on particle 3, and so on and so forth. Or maybe let's list all these observables. We have x1 tensor y2 tensor y3. We have y1 tensor x2 tensor y3. And we have y1 tensor y2 tensor x3. Good, maybe I should say that, but we'll come to that later. So these observables appear in the state with the correct signs. These observables appear in the stabilizer of the Greenberger-Horn-Zeilinger state. So Greenberger-Horn-Zeilinger state, maybe you remember that from the homework assignment, which may or may not have been due by now. I think it was. That's the Greenberger-Horn-Zeilinger state. Yeah, and so up to sign, these observables are in the stabilizer of that state. So that's the context in which you may have seen these observables before. But I'm getting ahead of myself. We are not talking about the state-dependent version yet. We are still talking about the state-independent version. Okay, so that was the first context. We have these 4 non-local observables here. Yeah, these 4. Okay, and now there's more contexts that have one of these 4 observables in it, and the rest is local observables. So for example, this guy, XYY, is x1 times y2 times y3. And likewise with the others. XXX is x1 times x2 times x3. Okay, so this is how the contexts are built. Good. Okay, and so now it's a similar version to what we've seen in the square. So from that perspective, it's not new, but it's a similar thing. So again, the point is that in the horizontal context, if you multiply these observables, you get minus the identity. And in all the other contexts, you get plus the identity. And so you get exactly the same type of algebraic contradiction that we had before. You have 5 equations now for the 5 contexts. You see every observable is at the intersection of 2 lines, at the intersection of 2 contexts. So every observable appears twice here on the left-hand side of the system of equations. Yeah, so you square it, you multiply all of that stuff, you get +1. You multiply everything on the right, you get -1. Same contradiction as before. So there's no value assignment. Okay, and that's not you, but it's not intended to be. Again, we wanted to morph something that looked like Mermin's like Mermin's square into something that looks like a Bell inequality. Okay, and that's that thing. So what's the starting point? So here, from this angle, it looks like Mermin's square. Okay, now we are going to move it over. Okay, and the first step in moving it over to something more like a Bell inequality is to make to introduce a state into the game. So far we didn't have it. We only had observables. Now we introduce a state. That state is the Greenberger-Horn-Zeilinger state of this form. And as soon as you have that state in, then these observables, they have values because the Greenberger-Horn-Zeilinger state is an eigenstate of all of them. And so for xxx, the eigenvalue is +1, and for the remaining 3, the eigenvalue is -1. Okay, so now with respect to the Greenberger-Horn-Zeilinger state, these 4 non-local observables do indeed have values. And the question is now, the remaining question is, can you assign values to these local observables such that you reproduce the eigenvalues of the GHZ state? Yeah, the answer must be no. We already know that. There was no value assignment for all of the observables. And then, well, we cannot suddenly get an assignment if we fix values for a subset of the observables. So we constrained a problem that previously didn't have a solution even more. So we're not getting a solution. So we already know that. Okay, but just so for clarity, let's look at this system of equations again. It's kind of completely the same type. So lambda of x1 times lambda of x2 times lambda of x3. So the product of these 3 values must be +1 because, yeah, the observables multiply to this observable which now has a value of +1. So these 3 values must give you that. And likewise, the values say x1 times y2 times y3 must give you the value of that, which is -1. Okay, so that's the second equation. Yeah, then you have 2 more for the other 2 contexts involving local observables. Okay, and then same type of argument, you multiply the left-hand side, you multiply the right-hand side. Here again, every observable appears twice, so you get +1, you get -1 on the other hand, so contradiction. Okay, so nothing new here except that this is beginning to look more like a Bell-type argument, because remember, the Bell-type argument was about local observables, and here you see values of local observables come up. So so that was not the case in Mermin's star. Mermin's star had local and non-local observables. Mermin's square had local and non-local observables. In Mermin's star, we could lift that. We could take all the non-local observables out and assign values to them. And so the question about values only remained for the local observables. Okay, so we are halfway to or almost there, in fact, at the Bell-type inequality. So like in the CHSH inequality, we're now looking at a certain correlation. And the correlation we are looking at is as follows. So we have the expectation value of xxx minus the expectation value of xyy minus the expectation value of yxy minus the expectation value of yyx. If you evaluate this for the Greenberger-Horn-Zeilinger state, yeah, value of 1 minus value of -1 minus value of -1, blah, 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 it evaluates to 4 for the Greenberger-Horn-Zeilinger state. So this is something you can reach in quantum mechanics. And if you work it out, which we are not going to do here in detail, it's a little bit more complicated argument, but of same kind, as we saw in case of the CH-SH inequality, classically you cannot exceed the value of 2. Yeah, so again, there is a gap between classical prediction, I mean prediction of the hidden variable model, and the quantum mechanical prediction. Yeah, and so that is now something you could measure if you wanted. Yeah, and so, okay, so then the morphing is complete. So now we have turned the contextuality proof into something that looks like a Bell inequality. Good. Okay, so I'm just mentioning this because Merman's star will come up a few more times here in this class, and Merman square too. Okay, so I just wanted to point that out. In homework 3 it was. I hope you have handed in homework 3 already. Good. So yeah, you saw this. Okay, so it didn't talk about hidden variable model and so on and so forth. But what you were calculating here was in fact referring to a hidden variable model. Yeah? And so you were reasoning about these models before they were even mentioned in class. Good. That I think it is. So I just want to end with a maybe a sociological comment. I don't know. Okay, it's causing some hilarity here, this plot. I don't know why. But I mean, it's kind of funny. So what's plotted here is the citation numbers of this paper. So they are quite high. Yeah? So it's reaching 700 citations per year. This is a very, very strong. But remember, the argument of the EPR paper would now be considered faulty because of the assumptions that, I mean, it's not faulty, but the assumptions that were being made would not relate to reality as we perceive it. Or, yeah? So it's the question of the conditional reality. So now we would assume that something like that exists and have no problem with it. And EPR just couldn't take that point of view. But so it doesn't seem to apply to the physical world as we have it around us. But even though the paper is in this sense a failure, at some point it began being cited like crazy. Yeah, so it was dormant, so nobody cared about it. Then people started caring about it a little bit, and then it somehow went completely crazy. Yeah, so maybe to end, so we can overlay this with the important events that happened in this field. Yeah, so there is the theorem of Bell and Kochen-Specker. So these are the two results here that rule out, Bell doesn't rule it out. Experiment distinguishes between the two. And that experiment was made by Alain Aspect in 1982 and co-workers. Then in between, in 1967, we have the Kochen-Specker theorem that says these hidden variable models are internally inconsistent. So they aren't even proper theories. Then we have the work of Mark Howard and company. So this is contextuality as a resource. So this is what we'll look at tomorrow. And then we have the Nobel Prize in 2022 for Alain Aspect, Clauser, and Zeilinger. Okay, so these are the important events. I mean, the important events that I could find relating to the EPR paper, but kind of, they do not really seem to mark the takeoff. Maybe if anyone does it, then it's the experimental test of the Bell inequalities by Alain Aspect. Okay, just wanted to mention that, and that is all for today.